So am I audible now?
Yes, yes.
Okay. Okay. What we'll do today is first we'll solve week four's assignment from last year, and then week three's assignment from this year. And then if we still have some time, so last time we weren't able to solve week one's assignment. So if we still have some time, we'll cover week one's assignment from this year as well. Okay. So is that fine?
Yes.
Yeah. Okay. So let's start. So the yeah. So the first problem is consider the following two statements. Statement P is that L is strictly contained in P space, and statement Q is that co-NL is strictly contained in NL. So choose the correct option. Which of these are correct? Both P and Q are correct. P is correct, but Q is not. P is incorrect, but Q is correct. And both P and Q are incorrect. So which of these are correct? Hello. Okay. Yeah. So someone is saying A is correct. Why is A correct?
Because NL is equal to co-NL according to the theorem. So therefore, co-NL is strictly contained in NL. So therefore, statement Q is correct.
Okay, wait.
And and
So if NL equals to co-NL, then we
mhm.
have this, right? So neither of
Yes.
these two containments is strict, right? So Q cannot be correct because of that, this theorem.
Yes, because
Right.
it is
So,
related
okay.
to the
Yeah,
strict
this is
containment.
strict containment, right?
Fine. And then
Yeah.
L is strictly contained in P space. So I remember that L is contained there within P,
Okay.
and P is there inside the P space. And so yeah, so therefore the statement P is correct. P seems to be correct.
Okay, but okay, again, over there is a strict containment. So do we know that P is strictly contained in P space?
So P is a subset of the P space, but P could be equals to the P space as well. So the may not be it may not be the strict containment. So
Okay. Yeah, so by arguing that P is in L is in P and P is in P space, we
mhm,
cannot prove strict containment.
mhm.
Okay. But there is another way to prove strict containment, and that is using the space hierarchy theorem. So space ah, so space hierarchy theorem says this, right? Hmm. If Fn is small o of Gn, then space D space Fn is strictly contained in D space Gn, right? Okay, so so what is L? L is P space log n, and P space is union over k greater than 1, P space n to the k, right? So in particular, P space contains D space n. Okay, and what we can say from the space hierarchy theorem is that D space log n is strictly contained in the space n, right? N is equal. This is strictly contained in, which is contained in P space. Yeah, so in this way we can show that L is strictly contained in P space. So is this fine?
Yes,
Yeah.
yes.
So P is correct and Q is incorrect. Which option is this? That B, right? Yeah. Okay, so the next problem is uh, out of the following given options, uh, select all the classes that are known to be contained in the class P. And the options are L, NL, sigma 2P, and pi 2P. So which of these are contained in P? Okay, so yeah, someone said A and B. A and B. Okay, so how is L contained in? So how are these contained in P?
L is contained in P because of that thing that so if we have been given Fn amount of the space, then we
Right.
require the time of the order of, say, more or less of the order of 2 raised to the power Fn.
Okay.
2 raised to the power
And
of the order of Fn. So now if we replace Fn by the log n thing, then we require
yes,
the amount of the time is polynomial.
correct. And what about NL?
So since yeah, so it doesn't matter that whether even if it is NL, then
Yeah.
also the machine will accept everything within these many number of the moves only.
Yeah. So basically, what you are saying is this: n n space Fn is contained in P time 2 to the order Fn, right? And L is contained in NL, which is equal to just n space log n, and this is contained in D time. So 2 to the order log n is like, okay, let me write it. And okay, 2 to, so what is 2 to the order log n? It's some polynomial, right?
Yes,
Yeah, so this is contained in, yeah, so it doesn't matter whether it's n space or d space, both work.
yes.
Yeah, so is this fine? Okay, so then let's look at the next problem. The next problem is, suppose we are able to show that TQBF is decidable by a non-deterministic polynomial time Turing machine, then which of the following statements can be inferred? P equals to NP, NP equals to co-NP, L equals to NL, and T space equals to NP. So which of these can be inferred?
So
Okay, TQBF is P space complete, right?
yes.
So if a P space complete problem can be solved in non-deterministic polynomial time, then what does that mean?
So but then NP is always a subset of the P space. So
Right.
what extra can we infer from here? We know that TQBF is there in the NP class.
Okay. How do we know that TQBF is an NP?
So TQBF is a variant of the satisfiability problem, only having some extra quantifiers.
Right. But okay, so because of those quantifiers, we don't know that it's an NP, right? Because if I were to use your exact same argument, I could argue that the language QSAT I, that is this language correspond that this language. uh, for there exists x1, x1 for all x2, phi x1, x2 is equal to 1. So this is the complete language of the second level of the polynomial hierarchy, right? This is complete for sigma 2. So using
Yes.
your exact same argument, I could have argued that this is known to be an NP,
Mhm. Okay,
but
okay,
that
okay.
would
So,
imply PH collapse, right?
yes.
Yeah, so TQBF is not a variant of SAT, and the reason is the following. It's for all quantifiers. So if, let's say, I give you an instance of TQBF, which looks like this. There exists x1, there exists x2, and so on. There exists xn such that phi of x1 to xn is 1. Then this is in SAT.
Yes.
But if I were to give you something like this, there exists x1 for all x2, there exists x3 for all x4, and so on. Phi of x1 to xn is 1. Then this is not in SAT. Or at least this is not known to be in SAT.
Hmm.
Because of the for all quantifiers. Because, okay, so what does SAT means? So phi would be in SAT if there exists x1, there exists x2, and so on, right?
Yes.
So in particular, it is possible that phi is in SAT because 1, 0, 1 followed by all zeros is a satisfying assignment. But 1 followed by all ones might not be a satisfying assignment, right? But if there was a for all quantifier in the second place, 1 followed by all zeros as well as 1 followed by all ones should be a satisfying assignment, right?
Hmm.
So basically, because of for all quantifiers, the TQBF is not the same as SAT.
Yes, yes. It is clear.
Yeah.
It is clear now. Yeah.
Okay.
So, yeah, this is element of sigma 2. So what happens that if so basically it shows that if what happens if sigma 2 is same as sigma 1. Does it mean like this? Because now it says that TQBF is in NP. So
Right.
NP means sigma 1. Is this okay?
Yes.
So but then TQBF is sigma 2. So what happens? So indirectly in
Wait,
this
why is
question,
TQBF sigma 2? Because TQBF is this, right? There exists x1
here, yes, and
for
for
all
all
x2. There
yeah,
exists x3 and so on.
I see. So yes, you're right. So it could be say, let us assume say TQBF is sigma I then. So
Okay. Again, there's a problem with that because if TQBF is sigma I,
yes,
uh, so PH is contained in P space, right?
yes.
Then if TQBF is sigma I, P space is contained in sigma I, right? But that we don't know.
I could not hear you properly, but then from here I understood that TQBF is sigma I, and if TQBF is known to be in
Okay, wait,
NP,
wait. What is
yeah.
sigma I?
So sigma
So
here
in
is
sigma I, there would always be I many quantifiers over here, right? Always,
yes,
regardless
yes,
of what this formula phi is.
correct.
But in
So
TQBF, is this if this formula had, let's say, two n variables, how many quantifiers would you have over here?
so if we have say n number of the variables, then there would be alternatively. So we would be having n by 2 numbers of the existential, n by 2 number of the universal. So there would be
Total n
2
quantifiers, right?
yes,
So basically in TQBF, the number of quantifiers depends on the number of variables and therefore on the size of the input, right?
yes,
In
yes. So
sigma I, the number of quantifiers does not depend on the size of the input, it's constant. That's the difference between TQBF and sigma I, or the complete language of sigma I.
right. So what could be the minimum number of the variables inside TQBF? Let us assume that
So
there is a
when we are looking
single
at TQBF, that is an increasing number, right? That is the size of the input. Or that's one way to measure the size of the input.
I could not hear this thing properly.
Okay. So in TQBF, the
Hmm.
number of variables, so the number of variables is a growing quantity, right? It is not
Yes,
constant. So we cannot say
yes.
that, okay, there would be minimum these many numbers or minimum these many variables and maximum these many variables. We cannot say anything like this.
Okay, okay.
Yeah.
Okay. So yeah, yeah, fine.
So TQBF is at least not, okay, so at least this argument does not tell you that TQBF equals to sigma I.
Okay, okay,
or
now I
TQBF
know.
is contained in sigma I.
Yes, yes, yes. Uh,
Okay, so all we need for this problem is that TQBF is complete for P space.
yes.
So using this, can you tell me which of these are correct?
So if all the problems which are there in P space can be reduced into this problem and which is now solvable in the polynomial time using NTM,
Right.
so it shows that all the problems, the complexity of all the problems which are in P space is same as the complexity of the NP class problem. So therefore, the last option, that is the P space is equal to NP, will become true for sure.
Okay.
And if P space is equal to NP is true, but then L is equal to NP, NL is more or less same irrespective of this argument.
Wait.
Uh,
No, no. Why is okay? More or less. Okay. So
yes,
L is. I think we discussed this last time as well, right? L is d space log n, and L is d space log n. If L
yes,
were d space log square n, then this would be true. Otherwise, this is not true.
yes, 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 right.
Right.
And what about this? So this, it is in NP and then P is equal to NP. So I think that we can only set the relation in between P space and then NP, and we can't say anything about the P and the NP as such, and neither we can say
Yeah.
anything about the NP and the co-NP as well. So I think
Okay.
that only
So
this option is correct.
okay. So you are partially right. We cannot say anything about P and NP, but we can say something about P and co-n and NP and co-NP. The reason is this. So in fact, the entire polynomial hierarchy is contained in P space, right?
Yes,
So if P space equals to NP, then co-NP is contained in NP, right?
yes.
But then, yeah, I think we saw a couple of lectures back that that also means that NP is contained in co-NP.
Mhm, mhm.
So that means both are the same, right?
Yes,
Yeah. So both B and D are correct. Is this fine?
yes. It's a very interesting
Yeah.
question. Yeah,
And
absolutely.
mainly, yeah, re- is this clear that TQBF does not a priori have anything to do with the sigma i's?
But still, I feel that we can always say that there would be at least a variable inside the Boolean expression. I mean, the Boolean expression say cannot be empty. If we put,
Okay,
if we consider this, so
right.
TQVF maybe we would as say sigma one union, sigma two, or union, sigma three, and then so on, depending upon the number of the variables inside the Boolean expression. So can we view it like this? In this form, that say TQBF is a union of the sigma I, wherein say I varies from say it may vary say from
Okay,
0
yeah.
to
I varies on I is in N. Okay.
yes,
Okay, so even this is not true because first of all, this class, the class you are saying, sigma 1 union, sigma 2 union, sigma 3, and so on, is exactly PH, right?
I see, yes, yes, yes,
Yeah,
yeah, yeah, you are right.
yeah. And so if TQBF were in PH, it has to be in some sigma I, right?
Yes,
But again, the same problem. It cannot be in any sigma I because the number of quantifier is an increasing function, right?
yes, yes.
Yeah. Okay, so if this is fine, we can look at the next problem. So the next problem is, suppose that all the languages in NP minus P are NP complete, then which of the following is or are true? P not equals NP, P equals NP, L equals NL, and PH equals P. So which of these are correct?
Uh,
Okay, so what does Lardner's theorem say?
So that says that there would be the presence of the NP intermediate problems. So there are problems which are in P, then there are problems which are NP, and there is an intermediate area.
Yeah, so it almost says that, but yeah, the exact statement, okay, the accurate translation would be this. If P not equals NP, then uh, NP minus P is not empty, right? Because an NP intermediate problem can only exist if P and NP are different, right? Because if P and NP are the same, there is no NP intermediate.
Yes.
Yeah. So Leibniz theorem says this, right? Now suppose that, so what do we have in the question? We have in the question we have that, okay, yeah. So in the question, what do we have? We have that NP minus P is empty, right? But then from the above theorem, P equals NP. Why? Because so the theorem says that P not equals NP implies NP minus P is not empty. So it's contrapositive. Is NP minus P is empty implies P equals NP. Is this fine?
Yes.
Yeah. So at least option B is true. If option B is true, option A cannot be true. Again, we cannot say anything about option C. And what about option D?
So yeah, option D would be correct.
Yes, it is correct, but why?
Collapse. I mean, the hierarchy will
Yeah.
collapse.
Yeah, so the hierarchy will collapse all the way to the first level, P.
Yes.
Yeah. So is this fine?
Yes. Yes.
Yeah. Then let's look at the next problem. So the next problem is consider the two statements. Statement P, 3 sat is in P space, and statement Q, 2 sat is in NL. And choose the correct option. Both P and Q are correct. P is correct, but Q is incorrect. P is incorrect, but Q is correct, and both P and Q are incorrect. So which of these is correct? Okay, so is P correct? Oh, oh, so you are saying that P is correct, but Q is incorrect, right?
Yes. P is correct because 3 set is in NP, and NP is there inside P space.
Okay, that is true. And
Yes.
why is Q false?
So 2 set is there in P, and
Okay.
this it is in P, but then we cannot say for sure that and this L and NL is there inside P,
Hmm.
and so do we know any relation in any exact relation in between P and L or P and NL, that P can never be equals to L, or
Oh, no, no, that is an open problem.
that is the open problem, right? So
Yeah.
there could be the case when P set requires the space and which may not be there in NL.
Okay. Okay, so in fact, it's already known that 2 sat is NL complete.
Okay, I was
Yeah.
not knowing this fact.
Yeah. So I think
So,
it was mentioned in one of the classes. And so, okay, what I can show you that 2 sat is an NL. There is so that I can show, but that proof is very long. And I
okay.
think that would easily take half an hour to 45 minutes. So,
Oh.
yeah, I mean, okay, it's very involved.
Mhm.
Yeah, so what I can do is that I can write, I've written it down. I can, like, along with the notes, I can put that as well in the folder.
Your video got freezed.
Okay. Okay, so what I was saying is, uh, the proof is very long. So if I show that, we won't be able to cover a lot of questions. So
Mhm.
what I can do is I can put that proof. So I've written it down. I can put that proof. I can add that proof to my notes and then upload the new document to the Google Drive folder.
Yes, yes, that would be fine.
Yeah,
That would be, yeah.
yeah. And then if you have any questions or doubts about that proof, you can either ask me in one of the sessions or in the forum.
Yes, yes.
Yeah.
So now my choice is the option D.
Still option B?
Option D, that both P and Q are correct. That
Oh, that is option A, right?
okay, yes, yes.
Yeah, D is both are incorrect.
Yes.
Yeah, so just let me note this over here that 2 sat is known to be an income. So, but okay, what I can tell you is basically this. Uh, the way to show that 2 sat is in NN is to reduce it to path. Or okay, path complement. Yeah, but both are the facts. Fine, because N equals co-n.
Okay, okay.
Yeah. Okay, so the next problem is consider the following generalized geography game between player 1 and player 2. I'll just call them P1, P2. Here the start node is A and player 1 goes first. Then which of the following is correct? Only player 1 has a guaranteed winning strategy. Only player 2 has a guaranteed winning strategy. Both player 1 and player 2 have a guaranteed winning strategy. And neither of them have a guaranteed winning strategy. So which of these is correct? Like, would you like to guess? Because this needs to be worked out.
So what is the meaning of the winning strategy here?
Okay, so player I wins if they can force player I plus 1, to enter a state from which they cannot leave.
Okay.
And by winning strategy for player I mean that player I should always be able to do this. So there exists a move for the first player, such that for all moves of the second player, there exists a move of the third player, and so on, such that the second player ends up in a state from where they cannot leave. That's the meaning of winning strategy.
Okay.
So it's
And
basically this. Regardless of what player two does, I am guaranteed to win.
okay, okay.
Yeah. Okay. So okay. Let me show you a winning strategy for player one.
So A to D, D to E, E to F.
Right. Yeah. So these are moves of player one. Player one plays A to D. So now you cannot visit A and D again. Now player two plays D to E. So now A, D, and E are off limits, and then it's player one's turn again, and player one plays E to F. So now when player two has to play, they cannot. There is no city, like there is no transition that goes out of F, right? So player
Yes,
two is stuck.
yes,
So that shows that player one, okay, all that shows is that player one is a guaranteed winning strategy, right? Not only player one is a guaranteed winning strategy. So the first
yes.
option is only player one has a winning strategy, but all we have shown is that player one has a winning strategy. What about player two? How do you show that player two does not have a winning strategy? Like, okay, think about this intuitively.
So if player one starts from A and make a move to say B, then player two can make a move to C. Player A will move to F then, and now the player A will get stuck there, and so therefore player two also has a winning strategy here.
Oh no, no, so it's not a guaranteed winning strategy, right? Because it depends on player one making a bad move.
Ah, yes, yes,
Okay,
yes,
so by winning strategy, what I mean is the following. Player I has a winning strategy. If regardless of what the other player does, player I can win. Okay.
yes.
So now think intuitively. If player one has a winning strategy, can player two have a winning strategy as well?
So if player one has a winning strategy, then no matter what player two selects, player one
Exactly.
is always going to win.
Right.
So if player one has a winning strategy, then clearly the player two cannot have a winning strategy.
Yes. Yeah. So that shows A is correct. So let us just formalize this that if player one has a winning strategy, player two cannot have a winning strategy. Okay. Okay. So yeah. Yeah, so when does player one have a winning strategy? So P1 has a winning strategy. So what this means is that there exists move 1 1. Okay, so what I'm going to do throughout the rest of the proof is this. I'll use Mij for the jth move of the ith player. Okay, so M11 is the first move of the first player. So there exists a move for the first player such that for all first moves of the second player, there exists a second move of the first player for all second moves of the second player and so on. M, uh, M11, M12, and so on is fine. Okay, so over here, where M is a Turing machine that takes input the moves and outputs one if player one wins and zero if player two wins. Okay, so this is exactly what we mean when we say that player one has a winning strategy, right?
Yes.
And over here, the Turing machine M exists for this game
Hmm.
because, yeah, I mean, give all the moves, you can just easily like execute those moves and see, right, who has won. Because a sequence of moves is just a path, and at the end of the path, all you need to verify is that I cannot go out.
Yes.
Yeah. Okay, so this is the meaning of P1 having a winning strategy. So now, what does it mean to say that P2 has a winning strategy? It's let me just copy this. Yeah, so P2 has a winning strategy if if regardless of what player one does, player two has a move. Regardless of player what one does, player two has a move and so on, right? And now this should become zero. So is this fine?
Yes. And why to write zero here
Oh,
instead?
so what does M do? M outputs one when player one wins, and M outputs two when M outputs zero when player two wins, right?
Okay. Okay. Yes.
So we are looking for a winning strategy for player two, so it should output zero because player two should win, right?
Yes. Yes.
Okay, now look at these two statements. They are negations of each other, right?
Uh, yes, not negation because in case of the negation, we should have placed a negation over M also, right? But then what could be the meaning of the
Yeah.
negation?
Okay, so this is negation over M, right? Negation. Okay, so what is this negation over here? Sorry, negation outside. So you are saying this, right?
So negation of outside would be that M produces zero as the output. Yeah.
Exactly. That is exactly this over here, right?
Yes.
Yeah. So P1 has a winning strategy. Yeah, I'm just writing what we just said. Is the negation of P2 as a winning strategy. Yeah, and so since P1 has a winning strategy, P2 cannot have a winning strategy. And that
Yes.
shows that option A is correct, right?
Yes.
Okay, so in this game, I only consider, okay, so look at the Turing machine M over here. It outputs 0 or 1 depending on who wins, right?
Mhm.
Now consider a game in which draws are also possible.
Okay. Okay.
So in this game, draws are not possible, but consider a game in which draws are possible. Try to do the following.
Your video got freezed again.
Okay, so what I'm saying is this. So in this game, draws are not possible, but consider a game in which draws are possible. And
Mhm.
what you can do is you can then say that M outputs 1 if player 1 wins, M outputs 2 if player 2 wins, and M outputs 0 if there is a draw. Okay.
Mhm.
What I want you to do is try on your own to show that for such games, even for such games, these two are negations of each other. But okay, that's not strictly speaking true. Okay. So try to show that even in those types of games, if P1 has a winning strategy, then P2 cannot have a winning strategy, and vice versa.
Okay. Okay.
Yeah.
But this is same as the TQBF problem. Only this.
This reduces to TQBS.
Yes.
Yeah, because yeah, so I mean I can use the ideas from the Cook-Levin theorem to convert this into a formula, right?
Yes.
Yeah, but what we do, okay, what is not immediately clear is that TQBF reduces to this, right?
Mhm.
Yeah, but in fact you can show that TQBF also reduces to generalized geography. That is so generalized geography is p-space complete.
Okay.
Yeah. Okay, so is that fine? Then we can move on to the next problem.
Yes. Yes.
Okay. Okay, I've moved on to the next page in my iPad. I can't see the next page in my computer. Maybe my reconnect. So which page can you see on the screen? Is it still the one with problem 8?
Yes. This is the problem 8 only.
Yeah. So in my iPad, I've moved on to the page with problem 9, but yeah, I think, yeah, so now it's the correct. Okay,
Yes. Problem
yes.
problem 9 is visible now.
Yeah. It's still a little glitchy, but it's yeah. Okay, so the ninth problem is which of the following statements is or are known to be correct? D time n square is in D space n square. D space n square is strictly contained in D space n square log n. D time n square is strictly contained in D time n square log n. And D space n log n is strictly contained in D space n to the log n to the 1.1. So which of these is correct? Or which of these are correct?
So first option is clearly correct.
Okay, yes,
And regarding the second one, so we'll have to see that whether so basically we'll have to apply the space hierarchy theorem here, I think,
yes,
and we'll have to check that whether this quantity is of the small o order of this n square is small o order of the n square of the log n of something, which I think is yes. So the
yeah,
second one
it's
also,
correct.
yeah, so second one would also be correct.
Yes,
And regarding this time, so for the time we require the now if we apply the time hierarchy theorem, then again I need something which is log n should be larger than by a log n amount. And
right.
again this is the case here. So C option is also
Okay,
correct.
wait. So for time hierarchy theorem, we need this, right? D time n square is strictly contained in D time n square log n, right?
Yes.
And over here we have n square log n.
Then will it make difference? I'm not sure. I'm not sure
Okay,
whether
so
this log of n square is the amount of the n or not.
Can you repeat that? Your voice broke.
Yes, yes. So whether this log of n is larger than this n square, larger than this, yes.
No, no, no. This
So
is no. Log n
yes,
is small o of log n.
yes. Is a small o of log n or not?
Okay, basically one very dirty trick. Okay, it's not so. Okay, so basically one way to check that log n is small o of log n is just do the following. Take the ratio and take the limit as n goes to infinity.
Yes, yes,
Yeah,
yes,
and like log n is clearly that limit is like zero, right?
yes,
Yeah,
yes,
so that shows you that log n is small o of log n.
yes.
Yeah.
So
So at least from the time hierarchy theorem, we cannot say that C is correct. And as of now, it's not known whether C is true or false.
mhm,
Yeah. And what about D?
should be off the order of, if I apply the space hierarchy here,
Right.
then
Yes. Uh,
I just need to show that this is a small o order of this thing.
right.
And so this 1.1 is such a small quantity, I think that in what it won't create that much difference. So probably the option D is not correct.
Okay. So, okay. So the question is this, like, is, with two brackets. So this is what we want to check, right?
Yes.
Again, just take the limit. What you would get. So yeah, let me write it. Limit n goes to infinity log n over log n to the 1.1 is 1 over log n to the zero point 0.1, right?
Hmm.
Sure, 0.1 is still small, but log n to the zero point 0.1 is still an increasing quantity, right? While 1 is constant.
Hmm.
So by taking n large enough, I can make this as small as I want, right?
I can take. I could not hear you this thing.
So by taking a very large value of n, I can make this quantity as small as I want, right?
Yes. Yes. Yes.
And so this limit goes to zero, right?
Hmm.
Yeah, so like this is true. Yeah. So this is true over here.
Yes.
Yeah.
So yeah, since it is true, so therefore this option is also true.
Yes. So basically, yeah, this trick almost always works. The only problem is sometimes the limit might not exist if you do things wrong. Yeah.
Hmm.
Yeah, but in most cases you would encounter this would work. So is this fine?
Yes.
Yeah. Okay, so the next problem is consider the problem of graph isomorphism, that is, deciding whether two given undirected graphs are isomorphic. As per the current understanding, graph isomorphism is known to be contained in which of the following complexity classes? The options are NL, P, NP, and P space. So which of these are correct?
So deciding whether two graphs are isomorphic or not. Probably we have some algorithm. Uh,
Yeah, that runs in time. That runs in quasi-polynomial time. So n
yes,
to the log to the O1. So like n to the log cube or something like that.
yes. So therefore this problem is in P.
Okay, wait. How is n to okay, uh, yeah, so we and n to the log to the kn time for I'm writing GI for graph isomorphism. K is some number. Yeah, I don't remember what the exact number is. K is something in N, right?
Hmm.
Now, what you are saying is this implies that graph isomorphism is in P. Why? So that would be true if this quantity per polynomial in N, right?
Yes, this quantity is
So is it
less
polynomial in
than or
N?
equals to uh, if this quantity is less than or equals to some constant.
N to the some constant, right?
Yes.
So
So
what we are interested in is in this, right?
is less than or
Let's
equals to
say,
say p.
oh, yeah, some constant P, right? So this is what we're interested in, right?
Hmm.
This would be in P, right?
So
Okay,
n is less than or equals to k raised to the power p.
wait. No, no, no. So we need log n to be that, right? This, right?
Yes, yes.
Yeah, and this would then imply that n is uh, 2 to the p to the 1 over k. Okay,
Yes, so but since p is a constant,
exactly. So p is a constant. This can be a very large quantity. Let's say if p were 10 and k were 1, this would still be very large, something like 1000, but it's still a constant, right?
so since it is a constant, so therefore the problem is in p.
Wait, oh no, so this is a constant,
Yes. So this is a
and
constant, so
there's a
therefore the
question mark
problem.
over here, right? So we are what we're asking is n less than equals to a constant?
So which is true, which is true.
Wait, how why is n less than equal to a constant?
Uh, I mean, because of this calculation that n is less than or equals to 2 raised to the power something, 2 raised to the
Okay,
power a
okay,
constant. Yeah.
okay. So everywhere in this calculation there is this question mark, right? So what this means is we are asking if this is less than equals to this,
Mm-hmm.
then we show that this less than equals to this implies that this less than equals to this, and it implies
Mm-hmm.
this less than equals to this, right?
Mm-hmm.
So this would be true if and only if this is true. So now the
Mm-hmm.
question is this true?
So I cannot think of any reason to consider it as a false value.
Okay, so what is n? N is the size of the input, right?
Yes.
And that is a growing function always, right?
Yes.
On the other hand, p is a constant.
Clear.
So let's say p is 10, k is 1, then 2 to the 10 is what? 1024, right? Just
Mm-hmm.
take n larger than, just take a graph with more than 1024 vertices.
Yeah, I understood. I
Right.
understood.
Yeah.
Yeah. So therefore, I mean, if you put a restriction here that we can have only less than 1,000 number of the nodes in between the two graphs, then
Yes.
probably we can solve the problem in the polynomial time. I mean,
Then we can
we
solve
can
the
solve
problem in
we,
constant time.
yes in the constant time, and thereby
Right.
may fall in this p complexity class. However, for a general case, it would belong to NP class then.
Okay. So what this tells us is that in general, we do not know if it is in P, right?
Yes.
But why does that imply that it is in NP?
Yes, so it is not in P, then we would be able to solve it in the polynomial time using. If
I
you
mean,
allow me to make
yeah.
guess, then I can. But then even if you allow me to make
I mean, you
yes,
are right. It's in NP.
if you allow me to make guesses, then I can solve this in the polynomial time.
Right. Exactly. You are right. But how? So what would be your guess?
So my guess would be that if you give me an assignment of the vertices that whether there exists a match with the other graph or
Yeah.
not, like I can do this thing in the polynomial time.
Right. So basically, if I were to give you a permutation and
Yes.
claim that G1 is isomorphic to G2 according to this permutation pi,
Hmm.
then you would be able to verify this fact in polynomial time, right?
Yes.
So yes, that is exactly the definition of NP. So GI is in NP.
Yes. And since it is in NP, so therefore the P space and the
Yeah,
NL may come automatically. Will come
P space
automatically.
is true. Why is it also in NL?
Because NL is there inside P, but then P is there inside NP. So if we so since NP is so NL is clearly NL is a subset of the NP.
Okay,
So NL is a subset of the NP. So therefore, uh, yeah. So NL is not necessary. NL is not
right.
necessary because NL is there inside NP and not
Yes,
outside.
yeah.
Yes.
So in fact, if GI were in NL, then it would also be in P, right? Because NL is contained in P.
Yes.
Yeah. So far, like, as of now, we only know that C and D are correct.
Hmm.
Some people believe that B is also correct. Most people believe it's not correct. Yeah.
Okay. So which is not correct?
Okay. So there are some people who believe that graph isomorphism is in P, but most people believe that graph isomorphism is not in P.
Okay. Okay.
In
Yes.
fact, it is a lot of people believe that it is a candidate for, it is a candidate for one of the for being a NP intermediate problem.
Okay. Okay.
So if P1 is not equals NP, then Ladner's theorem says that one such problem, one such NP intermediate problem must exist. And some people believe that GI is one such problem.
So can you suggest some reference wherein all the problems which are likely to be there in NP complete a list of those problems is given?
Okay, so there is okay, so there is no exhaustive list of all the problems,
Hmm.
but like there, I'm sure there are some like online, like there's some web pages which give you a list of sort of all of the well-known NP complete problems.
Okay. Okay.
I think I have that the link of that somewhere. Okay, what I can do is I can again I can add that to the notes or I can give you the in the next session.
Sure. Sure. Sure.
Yeah. Okay. So is this fine?
Yes. Yes.
Yeah. Okay. So then let's look at the next problem. So the next problem is let C colorable decide denote the problem of deciding if a given undirected graph is three colorable and consider the two below statements. Statement one is NT is contained in P to the three colorable, and statement two is co-NT is contained in P to the three colorable. So
Contained or
before,
sorry, contained or subset? It's not clearly visible.
oh,
Subset or
so
contained?
okay, so when I say that set A is contained in set B, I mean set A is a subset of B, right?
Okay. Okay.
So for an element, yeah, so if A were an element, it would be, I would call this containment. If A is a subset, I would call this containment.
Okay.
Yeah, yeah. So, but before I go to the options, do you know the meaning of this?
So is this the oracle thing that we do have the oracle of three colorability available to
Right.
us?
Yeah, so this is the class of all problems which
Mhm.
polynomial time Turing machines with oracle access to three colorable can solve. Okay,
Mhm.
yeah. So, and the options are only P is correct, only P is known to be correct, only Q is known to be correct, both P and Q are known to be correct, and neither of the statements are known to be correct. So, which of these is true?
So statement P seems to be true because we do have oracle access of three colorability, which itself
Right.
is NP class problem.
Yes.
And so now if I have the solution of the three colorability in one go, will it
Right.
help me to get the
Hello. Yeah. Can you hear me? Because I can't hear you. Your voice broke in mid. Okay. So, can others hear me?
anything? I will. Am I audible?
Okay.
Am I audible?
Yeah, you are audible now.
Okay, all right, yeah. And so clearly P option is correct. However, for the Q, if I can decide that whether this, if I can solve an instance of three colorability in one
Right.
go, then how will it help me to say something about the problems whose complement is there in NP? Will it
Okay.
help me to say something about those problems? Uh, so if I find the solution of the three colorability, how will this help me to solve those problems whose complement is in LP? That is not sure. So I
Okay.
can right now I can only say that the option P is correct.
Okay. So how would you prove that P is correct? You would do the following. Take any language in NP, reduce it to three colorable, which
Hmm.
you can do in polynomial time,
Hmm.
and then make one query to the oracle for three colorable, right? If it
Yes.
outputs zero,
Hmm.
the string is not in L. If it outputs one, the string is in L, right?
Yes.
This is how you would prove that NP is contained in three colorable. Now,
Yes.
what I'm claiming is this is both are true. Can you modify the algorithm that I just gave you for
Hmm.
co-NP,
So if the output generated by the oracle is zero, then the
right?
instance is not the element of the three colorability. So if the instance is not the element of the three
Right.
colorability, then it shows that its complement is, yeah. So
So basically,
yes,
X is not in L, so X is in L complement, right?
yes, yes, yes.
Right.
So
Yeah. So
yeah,
that's
so
yeah,
therefore the Q is also correct. Yeah.
yeah. Okay. I'll just write this down why Q is correct.
Yes.
So let L in quantity. Uh, L polynomial time reduces to three color complement. So consider a deterministic Turing machine, which, when given X, first uh, converts X. Okay, when given an instance X of L, uh, reduces it to an instance G of three colorable, and uh, it queries the oracle of three colorable. Oh, and instead of three colorable complement, because I want, yeah, because the reduction is from L to three color complement, right? So
Yes.
G is an instance of three color complement, but yeah, G is just a graph, so it's also an instance of three color. So it queries the oracle to three is query, then it queries the oracle of three color for G. If the oracle if the oracle outputs zero, then the TM outputs one, and vice versa. Right? The TM decides L because oracle outputs zero implies if and only if G is not in three color, which is true if and only if G is in three color complement, and this is this means that x is in L. Yeah, and when Oracle outputs, so when Oracle outputs 0 if and only if x is in L, and in this case, the Turing machine outputs 1. So the Turing machine decides L. Is this fine?
Yes, yes. So do we have immediate results available related to the oracles? Like say, if I have access to the oracle for the language A,
Hmm.
then do I always then will I always have an oracle for the complement of A?
Yeah,
Just
that is true. Because that is just this, right?
yes,
Can like query the Oracle for A at any string and just flip its answer.
yes. And apart from this, do we have other interesting results also related to the oracles?
Okay, so I'm not sure whether this was covered in the class this time or not, but using oracles, you can show that. Okay, so was Baker-Gill-Soloway theorem covered in this week or is it next week?
In the next week, in the week 5.
Okay, yeah. So yeah, so what Baker-Gill-Soloway theorem says is the following: using diagonalization, you cannot prove that P equals NP, or sorry, or P not equals NP, and that proof uses oracles.
Yes. So, I
Yeah.
mean, slightly related thing that since this Gill
Yes.
theorem is going to be covered in the next week, so would you be covering this diagonalization thing in the next week?
Yeah. So okay, yeah, I can let's say take the last half an hour of the next
Yeah.
week to cover diagonalization.
Yes, yes, that
Yeah.
would be really helpful.
Yeah.
Yeah.
Okay. So, but before that, like how much? Okay. Okay, what I can do is I can start covering from the very first use of diagonalization to prove that the set of real numbers is is much larger than the set of than the set of integers.
Yes,
Like, do you
yes.
already know that, or should I like do you want me to cover that?
So better you start this entire process from the beginning.
Okay.
Even you can give a proof that the halting problem is undecidable using the
Yeah. Okay. So
diagonalization thing
okay. So
if
what I'm planning
it suits to you.
do then is the following. First, I can show you this that reals are much the set of reals is much larger than the set of integers.
Hmm.
Then like uh, then tell you why that is called diagonalization and give a proof of halting problem using
Yes,
diagonalization.
yes,
And then formally define diagonalization because yeah. So even though initially diagonalization had a very limited meaning, that meaning was expanded later. And Baker-Gill-Soloway, the diagonalization in Baker-Gill-Soloway theorem is that expanded notion of diagonalization.
yeah, yeah.
Yeah. Yeah, so I think I can like do this for the last half an hour next time. Yeah.
That would be really helpful
Yeah.
if you can cover this. Yeah,
Yes.
fine.
Okay. So, oh, yeah. So, but is this problem fine?
Yes, clear. It's
Yeah.
clear.
So then we can move on to the next problem. And the next problem is out of the following options, which ones is or are equal to sigma pi plus 1, np to the q set I, onp to the q set I, np to the q set I complement, and conp to the q set I complement. So which of these are correct?
So since this is sigma thing, so it is related to NP.
Hmm.
And in case, so what this Q set here is a quantified satisfiability or is it same as
Hmm.
TQBF or some other thing? I don't
Oh,
know.
so this, okay, q set is the complete language. Yeah. Oh, q set I is the complete language for sigma I. So there exists for all that exists I many times and then a Boolean formula.
Okay, all right. So for NP and then for co-NP. So mhm. And since this is complete language for sigma I, and here we have been given sigma I plus 1. So show that we have been given an extra there existing, and because of this extra thing, uh, Not sure, but it will become CoNP QSET and the so I'll go for B and C. Then the
Okay,
complement of the QSET I and
okay. C
NP.
is correct, but B is not correct. It's A that is correct.
Okay.
Okay, here's the re. Okay, what did I do? Why did those disappear? Okay, yeah. Okay, so here's a quick reason. First of all, these two are the same. Do you agree that these two are the same?
Yes.
Yeah, because you could use the exact same argument that we used in the previous question, right?
Yes.
Okay. So now, if I give you an oracle for Q set I've also given you an oracle for its complement, right?
Hmm.
And
Yes. Yes.
okay, so what's the first quantifier of sigma IP? So basically, what I've done is the following. Forget about the first quantifier for sigma IP. Okay. Sigma I plus 1p.
Hmm.
Forget about that quantifier. Starting from the second quantifier onwards, you can sort of reduce that entire thing to this, right? Because if the second quantifier is again that exists, use this. The second quantifier is for all users, right?
This is not clear actually. You were
Okay,
not clearly audible. Yeah.
yeah. Okay, so the first quantifier of sigma I plus 1p is there exists, right?
Yes.
So to say, like, so forget about that quantifier for now.
Hmm.
From the second quantifier onwards, so the second quantifier is for all, there exists for all, and so on, right?
Hmm.
That you can sort of simulate using this, right?
Hmm.
And the first quantifier you can simulate using this.
Yes.
So since the first quantifier of sigma IP is there exists, we need NP over here because we want the first quantifier to be there exists, right?
So instead of sigma here, had this been a pi, then in
Then
that case the B and
these
D
two
would
would
have
have
been
been true.
correct.
Yes.
Yes. Okay. All right.
Yeah. So in fact, like this result is known, right? So this is just an alternative characterization of sigma IP. What is
Yes.
known is that these two are exactly the same. Yeah. I think this was should have been proved in class this time, or if it wasn't proved this time, it would be proved next time. I'm not sure.
It was covered in the class, but it was not that clear actually. It was covered
Okay.
in the class. Yeah.
Okay. So yeah, I agree. Like, okay, so this is difficult, but if you replace this with just sat, yeah, remove this and just replace this with sat and show that this is sigma 2, this proof is relatively simple. But
Hmm.
yeah, extending it to like this entire thing becomes a little complicated.
Yes.
Yeah. Okay, so that was last year's week 4 assignment. So now let's solve this year's week 3 assignment. Okay. Yeah. So the first question is which of the following is or are known to be true and select all the correct options. L is in P, NL is contained in P, NLE and QL are the same, and L and NL are the same. So which of these are correct?
ABC.
Yeah. A and B we already saw in a question this somewhere. And why is C correct?
Because of that theorem, Emerson's theorem, like, if I correctly remember
Yeah.
the name.
Immerman-Jeressen.
Lieberman's theorem. Yeah.
Yeah.
And the proof is really very well, horrible. The proof.
Yes. I mean, okay. So the idea, okay, so if you want to like, okay, okay, so if you want to give a very high level idea, the idea is relatively simple. So the idea is this. Okay, so what do you want to show? You want to show that path is in NN, right?
Hmm.
And you have the certificate definition of NN, right?
And I want
Right?
I could not hear. I could hear only till this point that path is NL complete.
Okay, yes. Okay. So what you want to show is that a path complement is in NL, right? Because then ONL would
Yes.
be continued in NL and you would be done, right?
Yes.
Okay. And you have the certificate definition of NL. So what you need to want to do is the following. Given a graph G and two vertices S and T in it, you want a certificate for the fact that there is no path from S to T, right?
Hmm.
And here's one way to do it. Suppose I had already convinced you. Okay, so let's think of this iteratively. Okay, suppose I had already convinced you that uh, there is no path from S to any neighbor of T, right?
Hmm.
Then it would be very easy for me to convince you that there is no path from S to T, right?
Can you please say it again? That.
Okay, so suppose I had already convinced you that there
Hmm.
is no path from S to any neighbor of T, right?
Any neighbor of S.
No, no. So there is no path from S to any neighbor of T,
Any neighbor of T.
right?
Okay. Yes.
Then
Yes.
there cannot be a path from S to T, right?
Hmm. Yes. True.
Okay, so what the certificate does is the following. It iteratively does the following. So it wants to convince you that S and T are not, there is no path from S to T. So it convinces you that there is no path from S to any neighbor of T. Then it
Yes.
convinces, to do that, it convinces you that there is no path from S to any neighbor of T and so on.
Yes. Yes.
Now,
Yes.
since like the graph has, let's say, n vertices, the length of any path can be at was n minus 1. Do this n minus 1 times. You would then have to convince me that, yeah, like there is no path from S to neighbor and neighbor n times of T, right? But that is
Yes.
just showing, that is it. For, to do that, all you have to show me is the following. That set and the neighbor of S are disjoint. That's it.
Yes.
Yeah, so the, the idea that's implemented in that proof is similar to this,
Hmm.
but the exact details become complicated. Because and the reason is you don't have too much space to store things.
Hmm.
Yeah. But yeah, the
Yes.
overall idea is just this.
Yeah.
Yeah. So is this fine?
Yes.
Yeah. Then let's look at the next problem. So the next problem is consider the language parity. Uh, the language is defined as follows. It's the language of all strings which contain an odd number of ones. Okay. Then which of the options indicate the space bound required for a deterministic Turing machine to decide parity? The options are order 1. Option B is order size of log x but not order 1. Option C is order size of log x but not order log of size of x. And option D is order log of size of x square, but not order order size of x. So which of these are correct?
So I require constant amount of the
Yeah.
space because I mean even I can write the regular expression for this.
Okay. Yeah, you are right. You can write a regular expression for this. But like, okay, either can you give me an order one space Turing machine that decides this, or can you tell me why a regular expression would imply this?
So because this parity can be recognized by a finite automata, deterministic finite automata,
Hmm.
and its size will definitely be finite, having the finite number of the states and finite number of the moves are required to decide
Okay.
that whether this string is a part of the language or not.
Hmm.
So because I require the finite, I mean, number of the iterations, so the space will definitely be finite. Just the log thing of the number of the transitions made over the finite automata. I
No,
mean,
no, no.
say if I require, say,
Okay,
to
then that would be a problem, right? Because in the finite automaton, you would make n transitions, right? At least n transitions.
Mhm.
One for every input symbol you read, right?
Yes.
So if you needed log of that space, then
Mhm.
option A would be true, right?
Yes.
Yeah, but the thing is this, basically regular expressions are in O1, and the reason is this, regular languages are in O1 because you have a deterministic finite automaton, and what you're going to do is you want to simulate that automata, right?
Hmm.
And to simulate that, all you need to save, okay, all you need to do is the following. First of all, you write down the description of that automaton on your work tape. That only
Hmm.
takes constant space, right? Because
Yes.
what's the description? All this, like all the states, all the transition function, and that's it, right? That is just constant.
Hmm.
So write that down on your work tape. Now you have a description of the automaton, and now you want to simulate it. All you need to do is save the current state, and that's it.
Yes, yes, and moreover, in the case of the Turing machine, so whatever I read from the tape, if I replace it by the same symbol, and if every time if I make a right move only,
Mhm.
so yeah, so that is nothing but a deterministic finite automata only.
Right. So if you read the input only once, then just
Yes,
make one pass on the input. Since it's the input type, you can't write on it. Since
yes.
it's, if you just make one pass of the input, which you are going to do while simulating this automaton, okay, but regardless of that, if you are just making one pass
Hmm.
and using constant space,
Hmm.
then yeah, it's a regular language.
Yes, yes, yes.
Yeah,
It's correct, understandable. Yeah.
right. Yeah. So uh, that shows that parity is in O1. Another way to see that parity is in O1 is just this. Okay, so okay, so for parity, you don't even need this automaton thing. That is a very simple thing. Actually, that okay. So I'm going to write an algorithm, but that is just going to simulate an automaton, a very particular automaton. The algorithm is this: uh, store a bit B on the work tape. Initially, P is one, and whenever okay, then make one pass on the input, flip P whenever you encounter one. Okay, so then one if then only is the number of ones in is O. Yeah, so is this fine?
Yes, yes.
Yeah. And so this is sort of simulating that automaton where you just have two states. One, so let's say A, Q0 and Q1. You are in state Q1 if the number of ones that you encountered so far is odd, and you are in state Q1 if the number of ones you have encountered is odd, right?
Yes.
Yeah, so this is just simulating that automaton.
Yes, yes.
Yeah. Yeah. Okay. So one more thing, we know the following, right? Let me write it down. So we know that okay, here let me just use B space. B space f of n is contained in d time 2 to the order f of n, right?
Yes, yes.
Okay. And over here we saw that this language is contained in order 1, right? So That means that there should also be a constant time Turing machine to decide this, right? So is my question clear? So over here,
So
Fn is order 1. So that means
mhm,
that there must be a constant time Turing machine that decides this language. But you need at least order and time to read the string, right?
mhm.
So there seems to be some contradiction over here, right? Because because since you need to read the entire string, you need at least order and time. But this says that you can do it in constant time. So why is there a contradiction over here?
Yes, yeah, that's true. Uh, so maybe because here we are, see, counting the space, we are taking the space occupied on the work tape
That is
computer.
always the case, right? We never consider the uh, space of the input tape, and if we only move from left to right on the output tape, then we also don't consider the space of the output tape, right?
Mhm.
So yeah, just because in this example we are only
But then,
considering the
this is true only when this fn is greater than log n. Is
yes,
this?
yes, that's the contradiction. That resolves the contradiction. Yeah, great. Yeah, so what I basically wanted to tell you was this, that there are examples where if this condition is not satisfied, this is not true.
Yes, this is an
Yeah,
important point. Yeah.
yeah. Okay, so the next problem is suppose the language N is decided by a non-deterministic Turing machine using space N, then what is the tightest bound one can get on the space on the space required by a deterministic Turing machine to decide N? The options are yeah,
So Savage theorem, direct result of Savage theorem, order of n square,
yes,
isn't it? Yeah.
yeah. So Savach's theorem says that if non-deterministic Turing machine decides something in space Fn, then a deterministic Turing machine would require space can decide it in space f square n. So here, what your n is like fn is just n, and so yeah, f square n is just n square.
So what is, I mean, which one is more appropriate to write, fn whole square or f square n?
Yeah, so generally it's better to write f square n, but if you remember from high school in trigonometry, we used to write sine square x, right?
Yes, 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 yes.
Yeah, so generally it's better to avoid this kind of notation because we also used to write sine inverse x, right?
Mhm. Yes,
And
yes,
over there, we did not mean 1 over sine x, we meant the inverse function of sine x, right?
yes, yes, right.
So it's better to write fn square, like fn
Yes,
the whole square.
yes.
But yeah, f square n is still written in like it's still a widely used notation.
Yeah.
Yeah. In fact, for that reason, a lot of people, so a lot of trigonometry books don't use sine inverse; they use arc sine.
Yes, you're
Right.
right.
So there's sort of that's the standard. You write sine square x and then arc sine.
Yeah.
Yeah. Okay, so then let's look at the fourth problem. So the problem is which of the following conditions are necessary for a language A to be NL complete? Select all the correct options. The options are A is in NL, A is polynomial time reducible to all languages B in NL. For all languages B in NL, B is log space reducible to A, and for all languages B in NL, B is polynomial space reducible to A. So, which of these are correct?
So A is clearly correct,
Right.
and B is correct. Uh, so A is polytime reducible. So all those problems which are there in NL should be reducible to this problem. And now I do not understand that what could be the meaning of the space reducibility, then that if A is polytime space reducible to B, because in case of NL complete, I don't remember that whether it was the time reducibility or the space reducibility.
Okay. So for NP completeness, we were using poly-time reducible, right?
Yes.
And what was the reason for that?
Uh, so
Okay, so suppose you could solve some NP complete problem in polynomial time.
mhm,
And what would that imply?
some NP complete problem in the polynomial time.
Yes.
Yes, so that would mean that all the problems which are there in NP can be solved in the polynomial time.
Yes, so that is P equals NP, right?
Yes.
Yeah. And why was that? Because the reduction was polynomial time, right?
Yes.
So for NP completeness, the question that the complexity theoretic question that we had in mind was P versus NP question. And so we defined a reduction that helped us with that question, right?
Yes.
So while defining NL completeness, what question do we have in mind? The L versus NL question, right?
Yes.
So now can you guess what the reduction should be? Polynomial space, polynomial type, or log space?
So it has to be log space.
Right,
So
because why?
so now because all the problems which are there in NP should be reducible to this problem A in the log space, because if it is the case of the log space, then this is polynomial too. I mean, the time would be polynomial, isn't it?
No, no, no. Okay, so the reason is this. Again, it's the same as what we saw in the P versus NP case. We want to argue if the problem we are interested in is in L versus NL, right?
Hmm.
So now suppose I could solve suppose I could solve an NL complete language in log space. Okay.
Hmm.
So suppose an NL complete language were in N.
Hmm.
Then again, if I were using log space reductions, I could say that uh, all of NL is in L. Why? Because start off with any NL language B, reduce it to A in log space,
Hmm.
and then solve A in log space, right? So the
Hmm.
entire thing would be log space,
Yes. Yes.
right? So
Yes.
since so while defining completeness
Hmm.
for any complexity class, we should have some complexity theory question in mind, and depending on that question, we would define reductions.
Okay. Yes.
Yeah,
Insightfully. Yeah.
right. So over here, it should be C, right?
Mhm.
So is this fine?
Yes. Yes.
Yeah. Okay, so now let's look at the next problem. The next problem is, suppose we define the complexity class exp as follows. Exp is the union over is the union from k equals to 1 to infinity of d time 2 to the n to the k. And which of the following theorems implies that P is strictly contained in exp? So in case this is not clearly visible, this is strictly contained. And the options are time hierarchy theorem, Savage's theorem, Ladner's theorem, and we don't know whether P is strictly contained in NP, XP. Yeah. So which of these is correct?
So yeah, and so maybe this may be because of the Leibniz theorem,
Okay, five.
but no, it says something else that NP complete.
Hmm.
So,
So in
but
fact,
I
Ladner's theorem starts off with an assumption, right, that P not equals NP.
yes, and so the only viable option left here is the first one, the time hierarchy theorem, I think.
Yeah, so that is true. Okay, there is another option as well. P not P. We don't know whether P is not strictly contained in EXP. But yeah, so the answer is time hierarchy theorem. That is true, but why?
So, uh, complexity class has been defined like this: the union of this thing,
Hmm.
and we want to show that P is strictly contained in EXP.
Right.
So, uh, yeah, so I cannot. So 2 raised to the power n. So if I put the value of n is equal to 1 here,
Hmm.
it becomes 2 raised to the power n, 2 raised to the power
Right,
n square. So, so clearly, I mean this, whatever I write here, n is a small o order of the exponential thing, right?
right,
So like
okay.
say n is a small o order of 2 raised to the power n.
Yes,
So maybe because of this, the requirement of the time hierarchy theorem is fulfilled here. So,
yes. But so
so
what you are saying is that n is small o of 2 to the n, but that only tells you that d time order n or d time n is contained in d time n to the 2 to the n, right? What you want to show is for all k, d time n to the k is contained in 2 to the n, right?
yes, 2 raised to the power n to the n raised
Yeah.
to the power
In
square.
fact, yeah, let me tell you, you just need to do the n over here.
But that is also true. That is also true. I mean,
Yeah,
we might be having the proof of that,
yeah.
that n
So,
square
okay.
is.
So what I'm saying is that if you use time hierarchy theorem
Mhm,
directly, you can only prove one thing at a time, right? So pick an L, you can only
mhm,
show that n to the L is strictly contained in d time to the n, but you cannot do this for all L simultaneously, right?
mhm.
But that is what we want over here, right? So my point is that using the time hierarchy theorem, you cannot directly get this result. So is this point clear?
Yes, yes, clear, clear.
Right. So then can you think, so, okay, so then why is the answer to this time hierarchy theorem? So all these show that is that this one way won't work, right?
Mhm.
So here's a way to do it. And it's also just using time hierarchy theorem once.
Yeah.
So what do we know? P is contained in d time n to the log n. Why? Because pick any language in P, it would be solvable in time n to the k for some constant k. K is constant, log n is not a constant, right?
Mhm.
So is this containment clear?
Not so clear.
Okay,
Probably I thought it like this,
okay,
that P is a subset of the D time n raised to the power k, and to store k, you require say log n number of the bits. So maybe because of that thing, probably you wrote here as n
okay.
raised to the power log
To
n thing.
store k, you need constant bits because k is a constant.
Yeah, this is
Okay, so
perfectly fine. Yeah, this is fine.
p is this, right? So now,
Yes.
no matter which k you pick over here, I so log n would be greater than k. Why? Because okay, this is a constant, right?
Yes. Yes.
And this is not a constant function.
Mm-hmm.
And we are talking, so like whenever we define these classes, we are defining them in the asymptotic sense, right? So you can put n as large as you want.
Mm-hmm.
Yeah, so now is this containment clear?
Yes. Yes. It's clear.
Right. D time n to the log n, right?
Yes.
Now, if I can show that d time n to the log n is strictly contained in ext, I am done, right?
Mm-hmm.
Now, uh, n to the log n is small of 2 to the n. So this is the same as n to the log. This, this is n to the log n times the log n plus log n, right?
Yes.
So
Uh,
okay, this is mm, mhm. Okay, yeah. So this is the theorem. Yeah. So what we want, so if you want to use the time hierarchy theorem, we need to show that this is small of 2 to the n, right?
yes,
And what is this? Is this n to the log n times log n plus log n. But this quantity is clearly less than n to the log n, right?
yes.
Okay, so okay, again by log square I only mean that.
Uh-huh.
Yeah. So in
Yeah.
fact, yeah, this is a so I'm approximating, and this is a very liberal approximation.
Hmm. Hmm.
The claim is this is small o of 2 to the n. Why? Because again, you can just take the limit.
Hmm.
Yeah, because okay, what is this? This thing is just 2 to the and yeah, and this this is still an increasing function of n, right? So as n approaches infinity, this approaches zero.
Hmm. Yes.
This this is this equality fine?
So I understood the gist of this proof,
Hmm.
even though I could not, I cannot recall, I mean, these logarithmic identities right now.
Okay.
Yeah, but then I have understood the gist of the
Yeah.
proof.
So basically, the gist is this: you wanted to show that P is strictly contained in X. You would show that a larger class is strictly contained in X.
Hmm.
Yeah. And the reason to go to that larger class is now we only have to worry about one function n to the log n is
Hmm.
instead of multiple functions n to the k for all values of all constant values of k.
Yes.
Yeah. Okay. So is this fine?
Yes, yes, perfectly
Yeah.
fine. Yeah.
Okay. So I think my battery is running low. So let me use one and charge the other. Okay. So the next problem is a language A is said to be in class L if there exists a deterministic Turing machine which decides A in space at most and mark all the correct answers. The options are order 1, order log n but not order 1, order log square n but not order log n, and order square root n but not order log square n. So which of these are correct?
So, yeah. Uh, so I think that ABC are correct,
Okay. Uh,
but uh,
A and B are correct. Why C?
so C is because log square of n is more or less of the order of. I mean, this is also a logarithmic space only.
Oh, no, no, no. Okay, so, okay, logarithmic space is just order log n. In fact, what you can show is this. Okay, so L is D space log n. So this is the definition of L, and uh, limit n goes to infinity log n over, okay, also again over here log square is just this log, this square, okay.
Mhm.
Yeah,
Okay. Okay.
yeah. So log square n is not log space, it's log square space. Okay, these
Mhm.
two are not the same.
Mhm.
Yeah, so then only A and B are correct. Okay, is this fine?
Yes. Yes. Yes.
Yeah. Okay, so the next problem is which of the following is or are definitely false, and select all the correct answers. The options are L equals NL, P equals NL, L equals P equals L, and P equals D time 10 to the 12. So which of these are definitely false?
Uh,
Yeah.
yeah. So regarding this L is equal to NL, this is an open question, isn't it?
Yes.
So this is, but we do not know. And then P is equal to NL. So again, we do not know for this.
Hmm.
And P is equal to L, we do not know for this again.
Right.
And what is remaining now is that P is equal to the
Yeah.
D time of
Okay.
n raised to the power. What is given here is
12.
12. Okay.
Okay, but okay, so that's one way to prove it. But okay, what's an actual proof of this fact that this is false?
What is the actual?
So what's an actual proof that this is false? This was previous year or earlier eliminated the options.
Yes.
Yeah.
So P is the, because this n raised to the power 12 is very much polynomial, and yeah, and P is equal to D time of this thing. But then this is false in the sense that it could either be the D time of simple n or D time of n square. Then why to strictly make it equal to the D time of n raised to the power 12 only, and not of the other powers, other exponents of n? So therefore, this statement is false.
Okay, but okay, so even if p were d time n square,
Yes, so
it would
P is
still be
equal to. So we cannot say that P is equal to the. I mean, according to the definition, it is not true. The P is equal to the union of this k varies from
right.
1
So the
to
question
infinite
is,
of the time of
is
n raised to the
are definitely false. So if you claim that this is false, you
power.
must be able to come up with a language in P which is not in d time n to the 12. Okay. So
Okay.
the question is definitely false, right?
Yes. So there
So can
there
you
could be
come up with
problems.
such a language?
So there could be problems which may not be solvable in the effort of the order of n raised to the power 12.
That is true, but how can you prove that such a problem must exist?
Yes. So that is the problem.
Yeah. Okay. So here's the answer. P is this, right? So P, oh, wrong. P time 10 to the 13 is also contained in P. Yeah, by the time. Uh, yeah, so P contains d time into 13, and P all. And from the time hierarchy theorem, we know that d time n to the 12 must be strictly contained in d time n to the 13, right?
Yes.
And so d time,
In fact, through this example only, now I understood the real importance of the time hierarchy theorem.
yeah. So by the way,
Yes.
okay, so here's again one sort of a paradox. Okay, suppose that three set were solvable. Okay, so my question is the following: why doesn't this imply that P not equals NP? And the proof I'm giving is this. Suppose P not equals NP. Wait, what do you want to prove? Okay, okay, no, wait. Okay, so suppose that you could solve a three sat in polynomial time. Okay,
Mm-hmm.
so first of all, this is true regardless of whether this is 12 or this is some arbitrary k, right?
Haha.
Okay, so now suppose you can solve three sat in polynomial time. So suppose P were equals to NP, and suppose you can solve three sat in polynomial time, right?
Mm-hmm.
Suppose you can solve three sat in n to the k time.
Mm-hmm.
Then all of NP should be contained in d time n to the k.
Yes.
But then P must also be contained in d time n to the k, right?
Yes.
But we know that P and d time n to the k are different. So that
Yeah.
implies that the original assumption that three sat can be solved in polynomial time must be false, right?
Yes. Yes.
So why doesn't this immediately prove that P not equals NP?
No, 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 no. There is some flaw. So you said
Yes,
that, yeah. So you said that three set is, see, if we assume that three set is solvable in the polynomial time, then all the
right.
problems in NP would be solvable in the polynomial time.
That is true.
Yes. So in that case, the P will become equals to NP. Where is a flaw in this?
Okay. What I said was this. Suppose three sat were solvable in polynomial time, say n to the k time.
Okay.
Then my claim was all of NP is in d time n to the k. This claim is false. All you can say is that all of NP is in P. I cannot say that all of NP is in d time n to the k. The reason is the following. How do I argue that if I can solve three side in polynomial time, I can solve all of NP in polynomial time? I would do the following, right? Start off the language N, reduce it to three side in polynomial time, and then solve three side in polynomial time, right?
Yes, but then, yeah, but then the point will be that if three set is solvable in the effort, say of the order of n raised to the power k, then
Right.
all other NP class problems will get solved in the effort of the order of n raised to the power k plus iota, k plus epsilon.
Not necessarily, right? Because what you can do is create a sequence of problems. Let's say P1, P2, P3, P4, and so on.
Hmm.
Okay, P is over here. P is P. Okay, so let's say you can create languages L1, L2, L3, and so on.
Hmm.
So that to reduce L1 to 3 stat, you need order n time. To
Hmm.
reduce L2 to 3 stat, you need order n square time, and so on, right?
Yes.
Then, like for a very large, let's say for Li, where I is very large,
Hmm.
you would need like n to the k times I time, right?
Yes.
And since I is increasing, this will keep on increasing.
Yes.
So just because 3 set is soluble in n to the k does not mean all of NP is soluble in n to the k. All you can say that all of NP is in P.
Yes. Yes.
And the reason I pointed this out was the following. So I think we have argued this I think we have used this intuitive argument a lot of times. Suppose a problem, let's say suppose a P-space complete problem reduces to a problem in NP, then all of P-space is in NP because, well, if a P-space complete problem reduces to, say, a problem in NP, then the effort required to solve the P-space complete problem is the same as the effort required to solve the NP problem, right? We have
Hmm.
used this intuitive argument a lot of times.
Hmm.
So the reason I pointed this out was That effort argument is only valid when you are looking at like broad things like polytime or log space, not when you are looking at exact quantities like n to the 12 or n to the k. Okay,
Yes, yes,
right. So
yes.
that so when you are working with exact quantities, you need to first come up with this intuitive argument and then formalize it to see
Mhm.
if it works. Yeah.
Yes, yes.
Yes. Okay. So then let's look at the next problem. Consider the following statements. D time n log n is strict. Okay. Again, both of these are strict containments. Okay.
Mhm.
D time n log n is strictly contained in D time n to the log 1.5 n, and d time n log n is strictly contained in d time n to the 1.5 log n. So which of these are correct? Both, none, or P is correct, but and P is going to be correct or Q is going to be correct. So which of these four options are correct?
So this is again related to whether this n of log n is small o order of this thing or
Right.
not. So I don't know, but then I think that both must be correct.
Okay, so P is not correct, but Q is correct. Okay, so okay, P is not known to be correct. It might be true, we don't know. The reason is the following. So n to the log n. So to show that P is correct, we need to show that this is true, right? Is this fine?
Uh, yes, yes.
Okay, but this thing is equal to, okay, this thing is, okay, let me write equal to first. Basically, if you have log AB is the same as log A plus log B. Okay,
Hmm.
and this is greater than into the log square n. Okay, again, over here, into this log square is into the log whole square. Okay,
Hmm.
same over here. Both of these are like complete powers. But this is, in fact, small omega of n to the log n.
Ah, yes.
Yeah.
Okay.
So the time hierarchy theorem does not tell us anything about P.
Hmm.
But what about Q? Well, the gap is in Q, the gap is n square root n, right?
Hmm.
Okay, so let me write that as well. So for, okay, this was for, and for Q, what do we want to show? N to the log n. So for Q, we want to show this, right? Now, this is order n to the log Q bed, okay? So we saw, so over here we saw that these two quantities are the same. So there is this extra quantity. What I'm going to do is I'm going to replace it by log n. So then this whole thing would become n to the log square n, right?
Yes.
But I'm going to say, okay, I'm going to be generous. I'm going to put a 3 over here. So this is clearly contained. So this is clearly contained in this, right?
Hmm.
And now again, limits. So what is this? This is log square.
Log square n divided by the root of n.
Oh yeah, root of n, sorry. Because log
Yes.
square n is much smaller than square root n, right?
Yes.
Yeah, so this is in fact true in this case.
Hmm.
So yeah, using the time hierarchy theorem, we can argue that Q is correct, but we cannot say anything about P.
Yes.
Yeah. Okay, so now let's look at. the next problem. I think let's make this the last one. So which of the following functions are known to be time constructible? And select all the correct options. N to the 1.5, n square, and log n, and 2 to the n. So which of these are time constructible?
Actually, this is not clear that how to know that whether a function is time constructible or the space constructible or not.
Okay,
Because
yeah,
in the notes they have written only one thing that most, I mean, commonly used functions are space constructible.
yeah. Okay, so I think the only way I know of it to show that a function is time constructible is to actually come up with an algorithm that constructs it in time in the appropriate time.
Hmm.
Yeah. So okay. Let me tell you one thing. All four are correct. To showing that A, C, and D are correct requires some effort, but showing B is correct is easy because okay. So what would you be given? You would be given 1 to the n as input, and you would have to compute n square, right?
Hmm.
In time order n square.
Hmm.
So all you need to do is convert that 1 to the n in u. That's an unary, right? Convert it to binary in order n time.
Hmm.
And then once you have n, multiply it with itself. That would also take order log n time.
Hmm.
So in order n time, you can compute n square.
Hmm.
Yeah. So n square is time constructible, but showing that n to the 1.5 n log n and 2 to the n are time constructible requires some effort. 2 to the n is still fine. 3 is to take too much time.
Hmm.
Yeah, because it's not clear how you would construct square roots and logs from a given string.
Yes.
Yeah. So yeah, all four are correct. This is easy to argue, but yeah, the rest are difficult. So yeah, let's not argue them.
Yes, yes, yes.
Yeah. Okay. So yeah, we're out of time. So let's end today. There was one good question that I wanted to solve, but yeah, fine. We can do it later. Okay. So next time we will solve like last year's Week 5 assignment,
Hmm.
and then only some questions from last year's Week 4 assignment, because if we solve all of them, then we won't have time for diagonalization. So is that
Okay.
fine?
Yes, yes, perfectly fine.
Yeah.
Yeah.
So there are no more questions, then we can end the meeting today.
Thank you so much.
Yeah.
I learned a lot in today's session. Yeah, thanks.
Yeah. Okay, so I'll just wait for a minute or so if there are any questions, and then yeah, end the meeting.
Thank you.
Yeah.
Yeah. Bye, bye,
Bye.
everyone.
Bye.
Bye bye.